Okay, let's get started. So I'm going to walk through problem 3B, which starts with the problem that is a person starts running with constant velocity trying to catch a streetcar that's initially, well, it says it in scientific notation, but it's 20 meters away from the person and has just started to accelerate from rest with a constant acceleration of 0.9 meters per second squared. The person runs just fast enough to catch the streetcar and hop on. So the first part of this was to describe a strategy you've chosen to solve this problem. But for part B, I'm going to walk through that and kind of assuming that you've already described the strategy. So what I'm going to do here for part B, which says, now show all your work in answering the following 3 questions. How long did the person run? What is the speed of the person when they just caught up to the streetcar? And how far did the person run? It's also going to be how far the streetcar traveled as well. Okay, so how I'm going to set this up is really with 3 equations and then just playing around with those equations. So the first equation, let's get a color here that I like. Let's use blue. All right, so the first equation I'm going to just set up right here is at the, I'll put these up in the corner, is at the position of the car, say delta S of car will equal 1/2 a delta t squared, and plus, we've done this before, the initial velocity, which we know is 0 times delta t. Well, I'm going to add something a little bit different to this, because we know that the change of position of the car, we know that it starts this change of position a few meters away from the person. In fact, it starts 20 meters away from the person. So if I want to describe the position of the car, this equation changes a little bit. And you can say that the position of the car, x, we'll just call that the position of the car, or we can just call it s. S of the car equals 1/2 a delta t squared plus any position that it originally started off with. So I'll just call that x. I'll just call that x sub 0 of the car. Okay, so I'm going to use this equation. That's just the position of the car. That'll be very helpful to us. I'm also going to talk about the velocity of the car, the streetcar, that is, velocity of the car, and that is just a times delta t. And so that's my number 2. This is number 1. That's number 2. And the third one I'm going to use is the position of the person. The position of the person, I'm going to say SP, S person equals the velocity of the person times delta t. Alright, so that's my third equation that I'm going to be using. Right, so that just shows position, which you should be able to see, the position of a person. That can be delta S, would be the change in position of the person, but the position of the person I just want to describe here. Okay, so I've got those 3 equations set up. Now what I want to do is I want to define as delta t. I want to define the delta t, and I can just shorten the delta t to t if I want to, since it's always going to be the change in time here. So the time that the person catches the streetcar, I'm going to call t catch. T catch. That's the time it takes. The time it takes for the person to catch the streetcar. So there has to be that some time in which a person does eventually catch that streetcar, and the streetcar is going to go faster than the person, but there's that small window in which the person can grab onto the streetcar and hop on. So what I want to do right now is I want to figure out what that time is, and at that time, we know that, I'm just going to use a different color here. At that time, we know that at t-catch, we know something special happens. We know that the position, oops, I'm using the wrong one here. So we know that the S car will equal the S person, because the person has to have the same position. We also know that the velocity at the particular time has to equal each other. So the V car also has to equal the V person. That's what happens at t-catch. So at that time, we know that the person is at the same position and the velocities are the same as well. Right. So what are we going to do now? I'm going to just start putting some equations together now. I'm going to say that let's see right here. Oh yeah, so at this, the position of the person, and the position of the car right here, I'm just going to fill out that equation using these equations right here. So for S car, I'm just going to put that in for this equation right here. So that turns into something else here. I'm just going to change that into this right here. So it's going to be, I'll use blue again. It's going to be this. It's going to be 1/2 A, now it's going to be T, you can say t-catch if you want to, t-catch squared plus, and then I put X there, plus X 0 car, and that equals the S of the person, which is V person times t-catch. Right? That makes sense. Right. Now I'm going to look at this one right here, the V car and V person. The V car and the V person. So the V person is constant the entire way through. The person is just having constant velocity. So we don't have an equation for that over here. We're just going to use this equation and plug it in here. So again, we've got, I'll just use black just to keep it constant. It's going over here. Blue. This is going to be, the V car is going to be A T catch. And then this will equal the V person. Right. So, now what I'm going to do is I'm going to try to make this a little bit simpler by replacing t-catch with these variables right here that we can maybe simplify later on. So let's try that. Let's try to simplify this into terms of t-catch. So that's just going to be V person over, and it's going to be A, and that'll equal t-catch. So I'm going to take this t-catch, so this t-catch right here, I'm going to plug it into these points right here and here. And we're going to see if we can then simplify the above equation just to figure out what the velocity of the person is in terms of the acceleration and the position. Let's see if that'll work. Okay. So here we go. All I'm going to do now is I'm just going to plug this in. It's going to be 1/2, and I'll try to use the same colors here. 1/2 A, and then black. Put the black over here so it's easier. Okay, 1/2. V person over A. Now this whole thing then is squared. Don't forget that. Squared plus the X0, the car that's the position that the car started from, streetcar. That's 20 meters away. We know that, but we don't need to put that in yet. We're just using a variable for it. And over here it's going to be v person times, now we have this, it's a different v person, well, it's the same number, but the v person that we replaced it with, v person over and over a. So I'll use that right here, over a. Okay, this whole thing multiplied. All right, now let's simplify this a little bit, shall we? Right. So this is going to simplify pretty nicely. We have, let's see here, 1/2. Wait. V person times this is going to be v person squared over a, I think, squared, yep, that squared, I'll just put a square up over that, over a, and then over here, let's see, what's going on over here? One of these a's will drop off, and it'll be 1/2. One of these a's will cancel, so it'll be 1/2 v person squared over a. Ah, this looks nice. Plus x 0 car. So that stays here. Right. So now to get, let's do this. Let's move this around so we can eventually cancel out everything and leave v person by itself. So I'm going to subtract 1/2 v person squared over a from this side, and that leaves me with x 0 car, that's the position of the car, equals 1/2 v person squared over a. That's nice. Now I'm going to multiply this side by 2 to get rid of that 1/2. So it's going to be 2x 0 car still. And then I'm going to multiply that by a to get rid of this a over here. And I'm going to take this square root. Ooh, I should make that a little bit easier to read. This car is still a subscript. 0 car is down below. And that whole thing is, so it's 2x 0 car times a. And then that's going to take we're going to take a square root of that, and that'll equal v person. Awesome. So now we got the velocity of the person. And that velocity of the person is going to be the same velocity of the car when the person catches the car. That's pretty cool. So now, what do we do? Now what do we do? Sorry, this is just a very long problem right here. I just want you guys to be able to follow this. So we've got the velocity of the person. That's awesome. That'll equal the velocity of the car. And the question, let me just check what the question asked. What's the speed of the person when they just caught up to the streetcar? So this is actually